Hey, what's going on, guys? Welcome back to the Mizu Study channel. I know it's been an extremely long period of time since I last broadcasted, but I'm back now. I think, I was in a bit of a rut. I was in a bit of a tough situation. Sometimes you just lose your kind of drive, like you ask yourself, like, why are you doing this, And I think it was just one of those reflections that I just had to do. But now I'm ready to hop back on the grind. There you go, nice. But I think I have a solid plan of exactly how I want to go about this. I think I know exactly what I want to do. And I think I know exactly how I'm going to achieve it as well. Whenever I start studying now, I'm going to start with, a topic that I genuinely have interest in, and then follow that up with something, whatever else that I like. Maybe I don't enjoy as much, but I have to get done, So that's exactly what we're going to do. It's a crazy amount of work to get through. It looks a bit like, but I think if we just take it one by one, I think we can do this, and I think it's going to be very extremely beneficial as well. So I'll stop yapping. We'll get straight into this. I'll start the timer as well, if you remember to do that. Okay, so I just need to get back into the flow, of things, and I know I can do it. So never gonna give up. There's gonna be times when, I feel as if I'm just gonna flick through all the stuff that I already did the last day, and then we'll continue on from there. So I'll keep my mic on. You can just mute me, because I want to just use this as me looking back on. In the future, I'm gonna look back on this. I'm gonna be like, yeah, I did that. So yeah, all right, let's start. Best of luck. All right, so we're studying a mechanics one, so physics. Mechanics one is, first of all, we start off with a vector. A vector is a quantity with both magnitude and direction. And for example, a force, a moment of force, magnetic flux density, electric field strength, velocity, displacement, acceleration. These are all examples of vector quantities, whereas a scalar quantity is a quantity that has a magnitude but no direction. Example would be mass, temperature, time, work, power, energy. These are all examples of vector quantities. So, scalar quantities. So then when we look at addition of a vector, is essentially if the vectors are going both in the same direction. Let's say I have force is a vector, right? Because it has both magnitude and direction. So if both of my forces are acting, let's say I have friction and air resistance, and they're both acting against, like if I have my mouse and my mouse is moving, they're both going in the same direction. I can just add them. For example, if I have 6 newtons and 8 newtons, that's 14 newtons. But let's say the force of this, it's falling down. So of course you have gravity that's pulling it down to the center of the earth. So that force is going down, that vector is going down, but air resistance is going up. So in actual fact, you add them, but you subtract the smaller one from the bigger one. So if the vectors are going in the same direction, you add them. If they're going in opposite direction, you subtract them. But you still add them, but you subtract them, basically. That's the whole kind of thing with that. Okay, so then we have the triangle law. If you want to find the if you want to add two vectors together. Then we have the different components of the vector as well. It's all Pythagoras, it's very simple. Then we have the demonstration experiment to find the resultant of two vectors. We place 3 Newton spring balances on a horizontal table with three pieces of non-elastic string, right? We're going to ensure that the strings of balance 1 and 2 are perpendicular to each other at 90 degrees to each other. We're then going to pull all 3 Newton spring balances. We're then going to ensure the point at which all of the strings are attached is now at rest. We're then going to read the magnitude of the force on each Newton spring balance and note the direction on which the forces are acting. I'm going to know that the vector sum of the forces 1 and 2 is going to be equal in magnitude to force 3, but it's going to act in the opposite direction. So essentially, we have a horizontal table. We have 3 Newton spring balances. You could say Newton spring balance 1, 2, 3. And then we have our non-elastic string and then a point of suspension as well. Don't forget that. So then we had these really interesting questions where we had a river, let's say. Let me grab another pen here. So actually, I'll probably grab it from my pencil case. But yeah, so we have a river, right? And let's say a boat, right, has a speed or a velocity, of 4 meters per second, and the river itself has a velocity of 3 meters per second. And we want to find out how long it's going to take for the boat to get from point A to point B. So you have that we find the hypotenuse, we find the angle in there, and we know that the distance between the two sides of the two banks of the river is 200 meters or whatever they will give us in the questions. We use Pythagoras, we find that hypotenuse of the big triangle. Then we use time equals distance over speed. We have distance, we have speed, because we found that we resolve the vector, and then whatever it is, chuck it in, you'll get your answer. Then there was another one where it was like, okay, if this is point B and this is point C, what will you have to do to ensure, or like at what speed, or how long is it going to take to get from the point A to point B exactly to point B? The other one was, oh, it wants to go from one side to the other side. Now it's specifically point B to point C. So essentially, instead of instead of the boat going like this way, the boat's going to go at an angle, and then the river is going to push down, and then we resolve that vector. But it's not going to be the hypotenuse this time, it's just going to be one of the sides. And then you find the angle between the hypotenuse and the horizontal, and then you say, oh, is it north of east? Yeah, it would be north of east. And then of course the distance is just 200 because you're going in a straight line. And then you do time equals distance over speed, and yeah. So again, we had a few definitions. So we said displacement is distance distance in a particular direction is measured in meters. Then we said, what is speed? Speed is distance over time. What's velocity? Displacement over time. What's acceleration? Final velocity minus initial velocity over time. That's what we said, right? Initial velocity over time. That's acceleration, exactly. So we had three equations of linear motion that we discussed. And these 3 equations of linear motion, the first one was v equals u plus at. So first of all, we're going to take our a equals v minus u over t, put the t, multiply it across, and you get v equals u plus at. That's fine. The second one was, okay, we need to get average velocity. So we have s over t, which is displacement over time, which is average velocity, and we have v plus u over 2, cross multiply, do everything, isolate s, you get ut plus a half at. No, sorry, another thing you need to do is you substitute u plus at for v as well, and then you should get ut plus a half at squared. Yeah, and then the last one is you take v equals u plus at, you square both sides, so you get v squared equals u plus at squared. You expand the binomial expression, and then wherever you have, so you're going to have v squared equals u squared plus 2a, and then you're going to have ut plus half at squared. You sub in your s, so you get v squared equals u squared plus 2as. So yeah, that was very good. And then we had the thing about displacement, right? So if I have like a semicircle, right, and I have point A and point B, that the displacement is going to be directly from point A to point B because it's distance in a particular direction. But my actual distance is going to be the circumference divided by 2 because it's a semicircle. So yeah. Then we had two types of graphs, right? We had displacement time graphs and velocity time graphs. Of course, displacement time graphs, displacement on the y-axis, time on the x-axis, displacement over time is velocity. So the slope of our graph is going to be velocity. So we had these different types of graphs here. For example, here, the slope. So we know the car does not start from rest over here because the slope is greater than 1, right? Because the slope, because if rise is equal to run, it's going to be 1, but it's greater than 1, so it's constantly speed is increasing. So it does not start at 0. It passes through the origin and it's moving with a uniform velocity because the slope is remaining the same. The slope is not curving like that. So yeah. Second one is that it does not pass through the origin, and we know that it has a uniform velocity, uniform speed. Here we can say that the car or whatever it is, the velocity is not increasing, the speed's not, so the speed's 0. So no, actually, sorry. So if I have a rise over run, excuse me, so if it's just flat, the car is stationary. Here is like the point of intersection. The x-axis, the x coordinate of the point of intersection is going to give us the time at which both cars are, one of the cars overtakes the other, and then of course the y-axis is going to give us the distance at which one car overtakes the other. We know that both of them do not start from rest, and both of them do not pass through the origin. So yeah, so they were analyzed at some distance after, and then of course we have this curve thing here, right? So this is means that the velocity is constantly changing. It's not a uniform velocity. So the velocity is increasing non-uniformly, is what you would say. And basically the only thing you have to know for this is that the slope will give you the velocity because it's displacement over time. Yeah. And then we have velocity time graphs where the slope is going to give you acceleration, velocity over time. And if you find the area underneath the graph, it's going to give you the displacement or the distance traveled by the car. So here, acceleration is uniform. It starts from rest because velocity is 0. Yeah. Here, the car does not start from rest, and the velocity and the speed is increasing. No, sorry, the acceleration remains constant. I mean, the acceleration is it's uniform, but it's increasing. Here, the car is moving at the same velocity because the acceleration is 0. Here the car is deaccelerating and the velocity is decreasing as a result. Here we can see that for the first period of time the car is accelerating uniformly. Then the car stops accelerating and the velocity remains constant or uniform, and then the car starts to deaccelerate. And here the acceleration is increasing non-uniformly. So yeah, exactly. And then we had our experiment. So essentially we have weights hanging off the edge of a horizontal table, which are attached to a trolley, right? And we know that the trolley is going to move to the right. The trolley may accelerate or move at a uniform speed. We know that the paper tape is attached to trolley and moves at the same speed as the trolley. You know, the paper tape is going to pass through the ticker tape timer. The ticker tape timer is going to put 50 dots per second into the paper tape. So 1 over 50. We know the time interval between each dot is 0.02 seconds. And if we examine these dots on this paper tape, we can determine, how long, the speed or the acceleration, the velocity or the acceleration, sorry. So if we have a uniform velocity, we'll take six spaces. If we have a non-uniform velocity, we'll take 5 spaces. And if you have acceleration, is we'll find u, which is 2 spaces, and then 2 by 0.02. And then we'll take 2 spaces here, right? And we'll be given the distance, and then we'll divide that by divide by 2 by 0.02, and then v minus u, we have our v and we have our u, so v minus u over t. What's our t going to be? From the middle to the middle. So this is going to be like 6 spaces. Or 5, sorry, 5, yeah. So there's also a light gates question as well. So it says, so what we're going to do is, to get our initial velocity and to get our final velocity, what displacement are we going to use? We're going to use the displacement as the length of the card. Yeah? And we've been given time. And we're given this. And we're given this. And then we use the distance that we use is this 80. Yeah. Yeah. So we have basically final velocity, initial velocity, and we've been given distance. So we get v, u, and s. So v, and we need to find acceleration. So we use v squared equals u squared plus 2as, and then we just calculate that. Then we have linear motion. So yeah, I think actually this is where we left off. Yeah, this is where we left off the last day. Okay, so that's what we call active recall, guys. Is that method of just blurting out everything you know. It's very beneficial. Honestly, it's a beautiful way of doing it, honestly. But yeah, so we're gonna go in now, so we're gonna go with sample question number 2, which is about a hailstone. And now we're looking at linear motion rather than horizontal motion, because linear motion, we have gravity, acceleration due to gravity 9.8 at play. So yeah, let's just go through. Wait, let me find a good pen first. So yeah, this pen is run out, so just throw it away. Okay, so essentially we have a sample question 2. This pen's also run out. Great. Honestly, if the pen is okay, yeah. It should work. Yeah, it works. Okay, so we have a hailstone. So first of all, we're going to have to do UVAST. So UVAST. So it says a hailstone is falling from a height of 2 kilometers above the surface of the earth. So your S is 2 kilometers. They want to trick you. You need to convert that into meters. So that's going to be 2,000 meters. And then, of course, it's falling down. So is acceleration due to gravity going to be positive or negative? It's going to be positive, because when it goes down, it's positive, yeah? So 9.8. Then it says, calculate the speed of the hailstone as it hits the ground. We know that V is going to be 0, because when it hits the ground, it's going to be stopped. It's going to be stationary. So what we really need to find is U. So what equation of linear motion are we going to use? We're going to use v squared equals u squared plus 2as. So v squared is 0, because 0 squared is 0. U squared plus 2as. 2 by 9.8 by hailstone from the speed of the hailstone. Yeah, wait, something's not. But then you can't find this. Oh, no, sorry. V is not 0, U is 0. So you should read the question. I was like, how? You can't get square root of a negative. That would be a imaginary number. Yeah, so V squared, so V squared is equal to 0. Yeah, and then 2,000. So let's just find the square root of that. So that's going to be 2 by 9.8 by 2,000, yeah? So V is going to be 197.99 meters per second. Don't forget your units. And yeah. So we have a note on terminal velocity, which we should probably learn. So, okay, what does it say? So we said as an object falls downwards, it accelerates due to the force of the Earth's gravity. Acceleration due to gravity. For example, if I have this, it accelerates. Like right now it's stationary, V is 0. No, sorry, U is 0. Yeah, so it accelerates. So we know that as an object falls downwards, it accelerates due to acceleration due to gravity. So due to the force of the Earth's gravity. So the force of the Earth's gravity is pulling it down. So the object is going to accelerate. So when an object is falling, it accelerates due to the force of the Earth's gravity, right? As the object's downward velocity, as the object's downward velocity increases, so does the value for the force of the air resistance. So if we're looking at this as vectors, you would minus them because one's going in this direction, one's going in this direction, but don't worry about that. So as the object's downwards velocity increases, its upwards air resistance also increases. The air resistance force acts upwards, as we just discussed. So the object falls faster. As the object falls faster, the air resistance increases until the upward forces equals the downward of air resistance equals the downward forces of gravity. When the up and the down forces are equal, the object stops accelerating, and now it falls with a fixed velocity called terminal velocity. So basically, as an object is falling downwards, right, it's accelerating because of the force of gravity, and as the object is accelerating downwards, and its velocity is increasing, so is the air resistance that's acting on it is also increasing, right? And this air resistance acts upwards. So you know that the velocity of the object continues increasing. The air resistance also increases until the upwards force of the air resistance is equal to the downwards force of the gravity. And when the upwards and downwards forces are equal, the object stops accelerating. And this is called terminal velocity. Basically, the whole concept of terminal velocity is when the downward force of gravity is equal to the upward force of air resistance, and the object's no longer accelerating. So yeah. So let's go with sample question 3. So a skydiver. So a skydiver falls from an aircraft that's flying horizontally. He reaches a constant speed of 50 ms minus 1 after falling to a height of 1500 meters. Calculate the average vertical acceleration. So UVAST is what we need. So here acceleration. Okay, so we know that if he's flying from an aircraft, if he jumped off an aircraft, initially he was at 0 meters per second. V is his terminal velocity, which is 50. Acceleration we want to find, and we'll be given the displacement as 1500. We have V, U, A, and S. We're going to use V squared equals U squared plus 2AS. So 50 squared is equal to 0 or whatever. 2 by 1500 by A. Yeah. So 50 by 50 is 2500 is equal to is equal to 3000 A, and then 2500 divided by 3000 is equal to A. So A is equal to equal to 0.83 ms minus 1. Yeah, it is actually. Yeah. And then we have another question here. It's the sample question 4. So sample question 4. It says that a golf ball moves at a speed of 30 ms minus 1 at an angle of 25 above the horizontal after being struck by a golf club. So essentially, for questions like these, yeah, you should always draw like a horizontal and a kind of like a diagonal line, yeah? So it's moving 30 meters per second, right? And it's moving at an angle of 25 degrees. So we want the greatest height reached, so we're going to go with the u vast. Yeah. So initial velocity is 30. Final velocity is 0. We want to find s, and we know our acceleration. I mean, if it's going up, it should be minus 9.8. So v squared is equal to u squared, so 30 squared, plus 2 by minus 9.8 s. Then I'm like, okay, 19.6 s is equal to 900. And I'm like, okay, s is equal to 900 divided by 19.6, and then s is equal to, okay, and I was like, okay, 900 divided by 19.6, which is equal to, excuse me, 45.92 meters. That's our first value. Then it says the time to reach this greatest height. So again, u vast. I mean, we know that it was 45.92. We fill in all the information we know. Minus 9.8. Final velocity was 30, and u was excuse me, u was 0. Yeah. And we want to find t. So we could just use v equals u plus at. So 30 is equal to u plus a minus 9.8 t. So then I have v is equal to u plus at. No, what happens if I use what did I use as my, oh sorry, yeah, I got it wrong, sorry. So v0 is equal to u plus at minus 9.8t. So 9.8t is equal to 30. T is equal to 30 divided by 9.8. T is equal to 30 divided by 9.8. 3.06 seconds. And then it says distance horizontally is distance is equal to speed times time. So I'll show you exactly what I do here. So it's actually 3.06. Oh, I was meant to resolve the vector first. Oh shoot. Y and x. Okay, let's redo that question, man. Oh man, I didn't realize, but yeah, I was like, why did they give us an angle, bro? I should have. It's okay. We all make mistakes. I haven't done this in a while, so I haven't done this in a month, 2 months, I think. So yeah, I'll give myself the benefit of the doubt. Okay, so we have a y and we have an x. That's the hidden step, kind of, even though it's not so hidden. And I'm putting the wrong angles. What am I doing? Okay, opposite and hypotenuse. So sine of 25 is equal to opposite over hypotenuse. And I'm like, okay, cos of 25 is equal to adjacent over hypotenuse. And I'm like, okay, 30 sine of 25 degrees is equal to y. Y is equal to, so 30 sine of 25 should be 12.68. And 27.19. Yeah, so we're going to use our y value for all of these calculations. Okay, UVAST, and this is our first. So it says, what is the greatest height reached? Yeah, so greatest height straight away is U. Yeah, so if we use my U value, right, my U value, we're going to use Y. So we're going to use 12.68. When you reach your maximum height, your velocity is 0. It's going to be minus 9.8, and we need to find S. So we're going to use V squared is U squared 2S. So it's going to equal 12.68 squared plus 2 by minus 9.8 S. Then I have 19.6 S is equal to 12.68 squared, and S is equal to 12.68 squared divided by 19.6. S is equal to yeah, so S is equal to 8.2 meters. Then it's like, okay, what time does it take? So if I have 8.2 and my time, I don't know. So I'm like V equals U plus 80. Okay, 0 is equal to 12.68 plus 80 minus 9.8 T. So I have 9.8 T is equal to 12.68. T is equal to 12.68 divided by 9.8. T is equal to 12.68 over 9.8, which should 12.68 all over 9.8 should be 12.68 over 9.8 should be 1.29 seconds. And distance, and I said, okay, distance is equal to speed times time, so 27.19 by 1.29 by 2, which is 2.58 is equal to multiplied by 27.19 is equal to 70.15 meters. I said 1.294 multiplied by 2 multiplied by 27.19, 70.37. Yeah, why is it giving me that shit? Yeah, okay, I got it finally. Okay, then we have a mandatory experiment here. So now we have a beautiful experiment here. And it could come up because the last time this experiment came up was 2023. Normal, like the actual paper, not the deferred. Which is a bit concerning. Yeah, so we have to be we have to be on it, like, you know, that way. But yeah, anyways, so we're going to measure acceleration due to gravity using free fall. So we have a soft iron electromagnet, we have a steel ball, we have a trapdoor, and we have a millisecond timer. So a soft iron electromagnet, a steel ball, a trapdoor, and a millisecond timer. So when the switch is on, so with the switch arranged so that C touches A, current flows through the electromagnet and the steel ball is held stationary. Move the switch C so that C touches B. The steel ball falls as the electromagnet has just been demagnetized. At the same time, the millisecond timer starts. The steel ball will hit and open the trapdoor. The millisecond timer stops. Measure and record the distance from the bottom of the ball to the trapdoor. Measure and record the distance from the ball. And record the time taken for the ball to fall this distance. The acceleration due to gravity is calculated using 2s over t squared. So 2s t squared. And yeah, so you get a straight line graph to the origin. So first of all, we're going to arrange the switch such that C touches A. A current flows through the electromagnet. The steel ball is held stationary. The switch is arranged so that C touches B. We know that the current stops flowing through the electromagnet and the steel ball begins to fall as the electromagnets become demagnetized. We know that the steel ball lands on and opens the trapdoor. So we know that the steel ball begins to fall. The millisecond timer starts. We know that the steel ball then lands on the trapdoor and opens it. The millisecond timer is then stopped. We know we're going to measure and record the distance from the bottom of the steel ball to the trapdoor, and we're going to measure and record the amount of time it takes for the steel ball to fall this distance, and then we use 2s over t squared. So we're going to let the ball fall 5 times for a given distance, and we're going to use the minimum value of time as recorded in your calculations. We're going to let the ball fall 5 times for a given distance, and we're going to use the smallest value for minimum value for time recorded. In your calculations, repeat the procedure for different values of distance fallen. We're going to repeat the procedure for different values of distance fallen. Repeat the calculations for each value of distance. Calculate an average value of g from all this data. Choose larger values of distance as smaller values lead to greater percentage errors. And avoid the error of parallax when measuring the distance with a meter stick. So essentially all they're saying is that carry out the experiment for a given distance 5 times and use the minimum value of time from your calculations. And then it's like, carry out the experiment multiple times using different values for the displacement. Use this distance to calculate several values of g to find out to calculate the average value of g. We're going to avoid using smaller values for displacement, and it leads to greater percentage error. And we're going to avoid the error of parallax when measuring the distance between the bottom of the steel ball and the trapdoor using a meter stick. So we know 2s over t squared. So we know straight line graph to origin verifies that 2 times the displacement distance is proportional to t squared. So basically, we're gonna draw this as well, yeah. Okay, so yeah, we have a little steel ball, we have a little soft iron electromagnet. Guess that's A, I guess that's B, I guess, sorry, something like that, I don't know. And then okay, and the battery's hooked up here. And it's like something like that. That's our trap door, I believe. And that's our millisecond timer. Yeah. So that's my steel. So that's my steel ball. So this is the acceleration due to gravity using free fall. This is my soft iron electromagnet. This is my trap door. This is my millisecond timer. So we're going to arrange for the switch C to touch A. Current flows through the soft iron electromagnet. The steel ball remains stationary. We're going to arrange so that the switch C touches B. We know the current stops flowing through the electromagnet and the steel ball begins to fall and the millisecond timer starts. We know the steel ball lands on the trapdoor and opens it. The millisecond timer stops. We're going to measure and record the distance from the bottom of the steel ball to the trapdoor. And we're going to measure and record the amount of time it takes a steel ball to fall this distance using our millisecond timer. So our precautions is that we're going to carry out the experiment 5 times for a given distance. So we're going to carry out the experiment 5 times for a given distance. And we're going to use the minimum value for time in our calculations. We're going to carry the experiment multiple times using different values for displacement or the distance between the bottom of the ball and the trap door. And we're going to use this to calculate several values for G and then find an average value for G. We're going to avoid the error of parallax when measuring the distance, and we're going with a meter stick, and we're going to use greater values for the distance, as greater values lead to smaller percentage errors, or smaller values lead to greater percentage errors. Okay, and 2s, G is equal to 2s over t squared. Straight line graph through the origin verifies that 2 times the distance is proportional to t squared, basically, yeah? Okay, and then, yeah, I just find the slope, okay. Oh, this is the fun stuff. It's not much to these notes, to be honest with you. Okay, so around Newton's law. So we know a body remains in a constant state of rest or uniform velocity unless acted upon by an external force. Unless a resultant external force acts on it. So you know that a body continues in a state of rest or uniform motion. A body continues in a... So we know that a body continues in a state of rest or uniform motion unless acted upon by a resultant external force. Unless a resultant external force acts on it. So we know that a body continues in a state of rest or uniform motion unless a resultant external force acts on it. So inertia, what is inertia? Inertia is a refusal to change their state of motion. Inertia refers to a refusal to change of a body to change its state of motion. It's the refusal of a body to change its state of motion. Definition of friction. Friction is the force that opposes the motion between two objects that are in contact. Friction is the force that opposes the relative motion of two bodies that are in contact, or two objects that are in contact. Then we have momentum. Momentum equals P equals mb. So P is momentum. Momentum is measured in kgms minus 2. M is kg. And then P equals mbv is ms minus 1. So kgms minus 1 is actually as a vector quantity. When a resultant external force acts on a body, the rate of change of momentum is proportional to this force and acts when a resultant external force acts on a body, the body's rate of change of momentum is proportional to this force. Newton, so and there's a derivation here, yeah. In the SI definition. However, the value of K is 1 in the SI definition of the Newton. Definition of mass. The mass of a body is a measure of its inertia. The mass of a body is its measure of inertia. Inertia is like of a body is its tendency to resist change of motion, its refusal to change its state of motion. So we know that law 1 states that a body will continue in a constant state of rest or uniform motion unless a resultant external force acts on it. We said that inertia is the refusal of a body to change its state of motion. We said momentum is equal to P equals mv. P is momentum measured at kgms minus 1. M is K mass in kg, and V is velocity in ms minus 1. Then we said the second law was that when a resultant external force acts on a body, the body's rate of change of momentum is proportional to this force. We said that as well. Then we had a beautiful derivation for F equals ma. So, which is based on this second law. So we said the definition of the Newton is 1 Newton is the force that gives a mass of 1 kg and acceleration of 1 meters per second. Yeah, so and friction is the force that opposes the relative motion between two objects in contact. Okay, so let's get this derivation underway. So first of all, we have force is proportional to rate of change of momentum. So force, alright, I guess F is proportional to mb minus mu over t. F is proportional to mv minus u over t. It's proportional to ma. F is equal to kma. K is equal to 1 in the SI unit of the Newton. F is equal to ma. So force is proportional to the rate of change of momentum. F is proportional to mv minus mu over t. We then factorize, so m is equal to v minus u over t. We replace the v minus u over t with a, so F is equal to F is proportional to ma. F is equal to kma. K is equal to 1 in the SI unit of the Newton. Then F is equal to ma. So the definition of unit, so a force of 1 Newton is obtained when a mass of 1 kilogram is given an acceleration of 1 meters per second squared. 1 Newton is the force that gives 1 Newton is the force that gives a mass of 1 kg and acceleration of 1 meters per second squared. Definition of mass is the measure of the inertia of a body, or its ability, its reluctance to change velocity. A weight, its body is the force of gravity acting on the body. So the mass definition of mass. The definition of mass is the measure of a body's inertia or its reluctance to change velocity. The mass of a body is a measure of its inertia or its reluctance to change velocity. Whereas, so that was mass. Weight is just the force of gravity acting on an object. The weight of a body is the force of gravity acting on the body. So mass is a body's reluctance. No, mass is the measure of a body's inertia or its reluctance to change velocity, whereas the weight of an object is the force of gravity acting upon it or acting on the body. So it says the first one is calculate. So sample question 1 says calculate the weight of, so W equals mg. W is equal to 0.2 by 9.8. W is equal to 0.2 by 9.8 is 1.96, and weight is measured in newtons. So for every action there's an equal and opposite reaction. Where's the third law? Oh, there it is. Then we have a sample question 2. So it says that a car of a mass 1200 kilograms is traveling east on a level road. Its engine exerts a constant force of 2.5 kilonewtons, causing the car to accelerate with 1.5 until it reaches a speed of 30. Assume the friction, so the net force is F is equal to 1200 by 1.5. What's 1200 by 1.5? Is equal to 1800 newtons. So the net force is the force of friction acting on a car is 2500 minus the 1800, which is equal to 700 newtons. If the engine is then turned off, calculate how far the car will travel before coming to a rest. we said 700 is equal to 1200 A. 700 divided by 1200 is equal to A. 700 divided by 1200 is equal to A is equal to 0.583, and 30 divided by 0.583 is equal to 51.46 seconds. It's definitely wrong. 8. So it says, yeah. So it says, if that's acting east, that has to act west. Don't forget. So that is what they give you. The friction is that minus that, because there's always a friction. There's always a friction. And then we have minus, which is what I got. And I was like, okay, u vast. It comes to a stop, so 0, 30. Acceleration is minus 0.583. So then s is what I want to find, and I was like 0 equals 30 squared plus 2 by minus 5.83 s. So I was like, okay, minus 5.83, no, sorry, minus 0.583 multiplied by 2. So I got 1.166 is s is equal to squared. So I was like, s is equal to 30 squared 1.166. So 30 squared over 1.166. So you got 771.87 meters. Yeah. Then we have an experiment here. Ding 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 ding. Okay. So we have an experiment experiment to show that acceleration is proportional to force. Remember in our derivation we said F is proportional to ma, so F is proportional to A, right? So experiment to show that force is proportional to acceleration. So same kind of thing, but the thing that's kind of weird here is we have our horizontal table, we have our low friction pulley, we have our non-elastic string, we have our weights at the end, we have a trolley, and a trolley and weights. So the trolley has weights on it this time around, and then same ticker tape timer, same paper tape. But yeah, that's it in a nutshell. So we have, so for this one, for force proportional to acceleration, we have a horizontal table, we have a low friction pulley, we have a non-elastic string attached to weights, which is attached to a trolley and weights, and a trolley and weights is attached to a paper tape, and the paper tape is then goes through the ticker tape timer. And yeah, so that's my ticker tape timer, that's my paper tape, that's my trolley and my weights, that's my non-elastic string, that's my low friction pulley, and those are my weights. So we know a force is applied to the trolley on the horizontal table, and the trolley moves with an acceleration. So we know that a force, so of course these weights are moving down, so we know that force is applied to the trolley, and as a result the trolley moves with an acceleration. So a force is applied to the trolley on the horizontal, table, therefore it moves with an acceleration. The force pulling the trolley is increased. So the force that's pulling the trolley is increased by adding more weights, by placing extra mass in the pan hanging off the edge of the table. The extra mass is transferred from the trolley to the pan to keep the mass of the system constant. So essentially a force is applied to a trolley on a horizontal table and moves with an acceleration, and if you want to increase the force pulling the trolley is increased by increasing the mass by increasing the mass of the pan that hangs off the edge of the table, and we know that this mass or these weights are taken from the trolley itself to ensure that the mass in the system remains constant. So the force pulling the so basically, sorry. So the force pulling the trolley is the weight. So we know that the force that's pulling the trolley is the weight of the weights hanging off the edge, is the weight of the mass hanging over the edge of the table, or the acceleration of the trolley is obtained by examining the dots on the paper tape, or the acceleration of the trolley is obtained using a data logger. Then calculation is you should record several values for force and corresponding values for acceleration, and plot a graph with force on the y-axis and acceleration on the x-axis. The graph is a straight line graph to the origin, proving that F is proportional to A. We know the slope of the graph is FA, which equals the mass of the body. So they're going to ask us. So we're going to keep the table horizontal to minimize the effects of gravity on the trolley. We're going to polish the table to reduce the effects of friction on the trolley. We're going to use a non-elastic string and a low friction pulley, and we're going to avoid using very small values for force, as this could lead to greater percentage error. So essentially what we're saying is we know that a force is applied to the trolley in a horizontal table and moves with acceleration. We know that the force that's pulling the trolley is increased by adding more mass to the pan hanging off the edge of the table, and this mass is taken by removing the weights from the trolley and adding them to the pan. This ensures the mass remains constant in the system. So we're going to measure and record several values for for force and the corresponding values for acceleration. And so we know that the force of the trolley is obtained by measuring the weight of the mass of that's hanging off the edge of the table, or by using the pattern of dots on the paper tape, or by using accelerations obtained by using the data logger. Then we have F on the y-axis, A on the x-axis, a straight line graph to the origin verifies that F is proportional to A. Then we had our 4 precautions. We're going to ensure that the table is horizontal to minimize the effects of gravity on the trolley. We're going to polish the surface of the table to minimize the effects of friction on the trolley. We're going to use a non-extensible string and a low friction pulley. And we're going to avoid using small values for force, as they lead to greater percentage errors. So to reduce the friction between the trolley and the table. Yeah, exactly. Law 3 to every action there's an equal and opposite reaction. to every action there's an equal and opposite reaction. To every action there's an equal and opposite reaction. Okay, to every action there's an equal and opposite reaction. Okay, so then we said, okay, now we have one of the most, I guess you could say, classic examples of the lift problem is actually a very classic example. So it says, a person of a mass 75 stands on the floor of a lift. Calculate the force the floor of the lift exerts on the person when the lift is at rest. So, excuse me. Yes, so 75 by 9.8 is 735. The lift is moving at a uniform speed of 5. So 1 and 2, being at rest and moving at uniform speed results in the same force. So if it's the same force, accelerating upwards at 2 is you have F minus mg equals ma. Because gravity is accelerating downwards, and then the next one's going to be plus. The direction of the acceleration is upwards. Upwards is positive. The direction of the acceleration is downwards. Downwards is positive. The direction of the acceleration, so the direction of the acceleration is upwards. So upwards is positive, which means gravity is negative. And here downwards is positive, so gravity is okay. So lift is at rest. F is equal to 75 by 9.8, which is equal to 735. If we move with a different velocity, that has no effect. 3 was like, okay, the lift is moving, no, the lift accelerates upwards at 2 ms minus 2. So force is equal to ma. So force, so the lift accelerates upwards. So upwards is positive. So ma is going to be positive. So the force that's going upwards is positive. So yeah, so F minus mg is equal to ma. F minus 735 is equal to 2 by no. The 885 newtons. So F equal minus mg, and over here we have, if it's moving downwards, so the whole structure of this is F mg ma. So F, which is our force, so the direction of the acceleration is upwards. So upwards is positive. So F is positive. So F has to be positive. But in the other cases, minus F plus mg is equal to ma. Is that right? I don't understand it like that well. So it's like, okay, so if the force is equal to the ma, so force is equal to ma, we know that, but then it starts accelerating. So ma, it's accelerating upwards, so ma is positive. So ma is positive, and if it starts accelerating downwards, then ma is negative. So if I have F minus mg is equal to minus ma, then I have Yeah, okay. Let's try that. So if the lift is accelerating up at 2 meters per second, I have F minus mg, but this ma is going to be positive. But then if I have, let's say it's accelerating downwards, I have F minus mg minus ma. Let's accelerating downwards. So F is equal to 735, F minus 735 is equal to minus was it 150. Then I get what is it, 585 newtons. So it's always F minus mg and then it's equal to ma if it's going upwards, because upwards is positive, and if it's going downwards it's negative. So F minus mg is equal to ma, and then F mg minus F is equal to ma. So if it's going upwards, it's F minus mg, and if it's going downwards, it's mg minus F. Nah, I need a better way. I don't understand. I'm not grasping it. So what is this though? This is the weight of the person who's in it. So ma is positive. So right now I'm saying the force of the floor of the lift exerts on the person. Right now I'm taking away the weight of the person, fine, because it's moving upwards. So ma is positive. But F minus mg, which is fine, but then it's minus ma. So it's F minus mg always if it's moving upwards, plus ma if it's moving downwards, minus ma. I think that's the best one. And then the support cable's break and the lift is in free fall. it's just mg minus ma, excuse me, is equal to F. Mg is it 75 by 9.8 minus 75 by 9.8 is equal to F. So F is just equal to 0 newtons. So essentially what we said was lift is at rest, F equals ma, very easy. Lift is moving at a uniform speed, doesn't matter if it's moving at speed, if it's at rest it's 0 newtons, the force that is exerting on the person. If it's accelerating upwards, it's F minus mg equal to ma, because ma is moving upwards, it's positive, and then the other one is F minus mg if it's moving downwards equal to minus ma, because moving downwards. Support cables break, force up because the force mg minus ma, same thing, 0. Okay. The conservation of momentum states that when two or more bodies interact with each other in a closed system, the total momentum of the bodies before the interaction equals the total momentum of the bodies after the interaction. When two or more bodies interact in a closed system, the sum of the total momentum of the bodies before the interaction equals the total momentum of the bodies after the interaction. So basically I have F minus mg is equal to ma, because ma is acting upwards, so that's positive. And acceleration is acting, if acceleration is acting, okay, let's just say, okay, my gravity is acting downwards and this is acting upwards, and I have F, I have mg, I have ma. Here ma, upwards force is positive, so that's minus. But here you see this, yeah, mg is negative, down and down, so I have F plus so that's positive, F mg equals ma. F is equal to ma minus mg. F is equal to ma minus mg. F is equal to here. No, I think I should just stick to my old one, which was F minus mg is equal to ma. If it's going up, accelerating upwards, F minus mg is equal to minus ma. If it's accelerating, alright, so if it's going upwards, ma is positive. If it's going downwards, ma is negative. And then F equals F equals mg minus ma. I said F minus mg, so I was just revising. I just didn't understand this concept. So like, of course, I have a method of remembering. It's like F minus mg is the same, but if the acceleration is going up, it's positive ma. If acceleration is going down, it's negative ma. Okay, so the conservation of momentum, the law of conservation of momentum states when two bodies interact in a closed system, the total momentum of the bodies before the interaction is equal to the total momentum of the bodies after the interaction. So basically what we're saying is m1u1 plus m2u2 is equal to m1v1 plus m2v2, where m1 m2 are the masses and u1 u2 are initial velocities, v1 v2 are final velocities. So basically we have a sample question here. It says a particle of a mass 10 kg is moving at a velocity of 4 meters to the right and collides with a particle of mass 5 kg moving at 1 to the left. After the collision, the 10 particle moves at a velocity of 2 meters to the right. Calculate the velocity. So basically we're saying 10, a particle of mass 10 kg is moving at a velocity of 4. Yes, that's my m1u1 to the right and collides with a particle of mass 5 moving 1. So plus 5 moving to the 1. Yeah, and that's equal to, after the collision, the 10 kg particle moves with a velocity of 2. Yes, and then the 5 is just v, so we don't know. So 40, so we have 45 minus 20 is equal to 5v. We got 25 divided by 5 is equal to v. V is equal to 5 ms minus 1. And if it's 5 ms minus 1 to the right, I think. Oh, sorry. Oh, shoot. Oh. Sorry. Totally messed it up. So that's moving to the right. Okay, so that's 40 minus 5. That's 35. 35 minus 5 is 15. 15 is equal to 5v. V is equal to 3 ms minus 1. Yeah? So v is equal to 3 meters per second. But v, it's positive because we're taking the positive velocity to be moving to the right. So we say to the right. Yeah, because basically we're saying, okay, what are we taking as positive? We're taking as positive, move to the right. We're taking as negative, move to the left. So that's why when they said it's moving with 1 meters per second to the left, we denoted that as negative. So, and it's like, okay, there's a bullet, right? And the bullet is moving, it's a 2-gram bullet, which meaning we have to convert it to kilograms. So in kilograms, a crude bullet is like 0.002 and then multiplied by 360, of course, and it hits a stationary piece of wood, so 0 by 0.9, which is just 0, and then that is going to equal, becomes embedded in it. Okay, so their masses are added to each other. So 0.902, yeah, and it says, but v, now we have that, yeah? Anyway, so we have 0.002 multiplied by 360. Yeah, so we have 0.72 is equal to, no, divided by 0.902 is equal to v. If I divide this by 0.902, I get, yeah, I get v is equal to 0.798 ms minus 1. And it says, yeah, so then we had a, so we have a spacecraft. This one got asked in a class test as well, I remember. We have a spacecraft of a mass, and it has 1200 mass. So for part I says the gas is expelled in the same direction. Okay, so we'll discuss that. So we've done that, and it expels a gas. So what I'm going to tell you, and don't think too much about this, but the gas is expelled in the same direction. If I am going this way and the gas expelled this direction, it's going to push me in the opposite direction, right? So the velocity is actually going to be negative 420. I know it sounds weird. And then, sorry, then because we've lost 80 kg, it's actually going to be 11,920, and then we have to find our final velocity. So if we take 12,000 minus 80 by 420, minus 80 by 420, yeah, okay, so we have 1200 sorry, 1200 move velocity of 1 plus 80 by 4 is the velocity, yeah, the velocity is, yeah, so 11,920 v. So I was like plus so I got minus 21,600 is equal to 11,920 v. Divide by 11,920, we get rid of that, v is equal to, divide by 11,920, we get minus 1.81 ms minus 1. And then here we have 12,000 plus 80 by 420 divided by 11,920. So we have basically 3.826 ms minus 1. So this is moving to the right, and we can say this is moving to the left. So yeah, so 1.81, yeah. Yeah, so that's moving faster, but that's going reverse. So if it's in minus, basically, even if we look at that formula that we had for, I mean, what was it? The one that was a equals minus omega squared s. The minus indicates that the acceleration is acting in the opposite direction to the displacement first. Yeah, so that's kind of the thing, yeah. Yeah, okay, I'll probably finish up on this. This is a sample question. So sample question 4 is saying that there's a boat of, so there's a boat of 1,000, right? So we have 1,000 and it's moving with 5 meters per second velocity, and we have a cannonball 20. So we're moving north like this, and we have 1,005, and then a cannonball of mass 20 is fired from the boat due east. So we have a cannonball and it's going That's west. That's east. Sorry. That's east. That's east. So that's 1,000 by 5. That's 20 by 200. This is a very techy question. Yeah. So basically, I need to just look at the solution. So momentum of the cannonball is m by v. So m is 20, 204,000 kgms east. The westward momentum of the body is 4,000 west now. The westward velocity of the boat is v equals p over m, which equals this. Now we must add a velocity of 5 north to the velocity of this west. And basically, yeah. So does the 1,000 even? No, it does matter, yeah. Okay, so basically what we're saying is, first of all, we need to find the momentum. So P is equal to 20 by 200, which is equal to 4,000 kg ms minus 1. And this is moving east. So that's 4g, yeah. So the total momentum of the boat towards the east is 4,000 kgms minus 1. Now we have P equals mv. We have V is equal to P over m. We have V is equal to P. P is the momentum, which is 4,000. But then we know that the mass of the whole boat, because a cannonball weighs 20 kgs and we've gotten rid of that, it's 1,000 minus 20, which is 980. And then we have V, which is equal to, and then we can just chuck that into our calculator, divided by 980. Yeah, so that's 4.08 ms minus 1. But then we need to find the new velocity of the boat. So there's gonna be a bit of components of vectors and all that. So we have to add two vectors together. We have one vector, which is our velocity. Velocity is a vector because there's both magnitude and direction. That's moving north, 5. And then we're moving east at the same time. Sorry. We're moving east at the same time at 4.08. And you find this. So we got x squared. Let's just say x squared is equal to 5 squared plus 4.08 squared. Then I'm like, okay, x is equal to the square root of 25 plus 4.08 squared, which was 16.6464. And I'm like, okay, square root of 25 plus 16.6464. X is equal to 6.45. Don't forget your unit measures, which are meters per second. And remember, it's velocity. Velocity has both magnitude and direction, so we have to give the direction as well. So we're just going to do SOHCAHTOA. So we're going to do opposite adjacent. So we're going to get tan of theta is equal to opposite over adjacent. So 5 over 4.08. So theta is equal to the tan inverse of opposite over adjacent, like that. So theta is equal to, let me make sure my calculator is in degree mode. The inverse of tan is going to give us 5 over 4.08. And we should get 50.78. 50.79 degrees. And because we're going north and we're going east, it's going to be north of east. So north of east. Nice. Oh no, wait, I messed up something. If the momentum of the cannonball is east, the momentum in the opposite direction has to be therefore west, yeah. So in actual fact, it should have been like that. Oh, but yeah, so north of west. So if my momentum east, because momentum, so when two bodies interact in a system, in a closed system, the total momentum of the bodies before the interaction is the total momentum of the bodies after interaction. So 4,000 when it's ejected, 4,000 before, 4,000 in this direction, 4,000 this direction, 4,000 this direction. And then we find our velocity. We add up the two vectors. We get the hypotenuse, we use that, we calculate the angle between the hypotenuse and whatever, opposite, adjacent, whatever, SOHCAHTOA, man. And then you have west, you know the momentum in the west, because of course it's the same as the gas being ejected from the spacecraft. If I eject it in the same direction, the spacecraft is actually going to push in the opposite direction. So it's going to be north of west, not north of east. Oh my god, that was a whole thing. This is my story. Been working for a good amount of time, like. Okay, then. So we have a mandatory experiment to demonstrate the principle of conservation of momentum. To verify, sorry, the principle of conservation of momentum. So this was last in 2020. 2020 was you had the choice to do the leaving cert or not. And then deferred 22 and cheeky 25 as well. So it most likely won't come up, but it's still good to have it because these examiners are so unpredictable. It's the last year of the course. They can put anything they want. They're going to be emptying out the drawers, basically, in a nutshell. To be honest, I could probably just get this whole chapter finished. Yeah, I don't have much left. Okay, so mandatory experiment. So we want to verify the principle of conservation of momentum. So we have a before collision. Before collision, of course, we have a trolley. We have two trolleys, and we know that, for example, when we shot the bullet into the plank of wood, yeah, they became one body, you know, so they had the same velocity, both of them, because they're stuck inside it, because the bullet was stuck inside of the plank of wood. Same thing happens here. So basically, we have two trolleys. We have Velcro at the end of the two trolleys, and one of the trolleys, the first trolley is attached, has a paper tape attached. Paper tape, of course, going to move with the same velocity as the trolley, and it has a ticker tape timer. And of course, then we have the horizontal table as well. And then after the interaction, they attach because of the Velcro. Yeah. So we're going to arrange for one trolley to move at a uniform speed. So that's probably the first trolley with the ticker tape timer attached and paper tape and all that. So it collides and sticks to the second trolley, which is stationary. So it's U1, it's U2 is 0. So we're going to arrange for one trolley to move at a uniform velocity. And this trolley that's moving at uniform velocity is going to collide with another trolley that's stationary. It collides and sticks because it has Velcro. The trolleys join together and move along the table, and the Velcro attached to the trolley allows them to join together. We're going to measure and record the masses of each trolley. These will be M1, M2. We'll measure and record the velocity of the first trolley before the collision U1, and measure and record the velocity of the joined trolleys after the collision, which is V, because now they're one unit, you know. So all the recorded data is substituted. So instead of using M1, U2, M1, V1, M1, V1, M2, V2, instead of using that stinky formula, we're going to be using M1, U1 is equal to M1 plus M2, because now both of the trolleys are joined together. Their mass is like 1, yeah? And the velocity is going to be the same as well. So that's fine. So we have M1, U1, and then because we calculated U1, by calculating the speed of the trolley with the velocity of the first trolley before the collision, and then the velocity, and then record the velocity of the joined trolleys after the collision V. So we're going to arrange for one trolley to move along a horizontal table with a uniform motion. This trolley is going to collide and stick to another trolley which is stationary. We're going to arrange for this trolley to collide with another trolley that's stationary. We know that these so these trolleys collide and stick together, and both of these trolleys stick together through their use of Velcro, due to their Velcro, right? So we know that we're going to measure and record the masses of both of these trolleys, which is going to be M1, M2. We're going to measure and record the initial velocity of the first trolley before the collision, U1, and find the velocity of the joined trolleys after the collision, which is B. So then we have that as well. So we're going to have M1 U1 equals to M1 plus M2 V. Yeah. Equation should show that momentum before the collision equals momentum after the collision, verifies conservation of momentum. The numerical values on the left and right might be little due to experimental error. So we allow for experimental error. So the reason why the value on the left might be a bit different to the value on the right is because of the experimental error. And we know that the value on the left should be equal to the value of the right to illustrate that we verified the principle of conservation of momentum. So it's an approximation, but because we allow for experimental error, sorry, I dropped my pen somewhere. Oh. Yeah, so of course, same drill. Bro, this is like a whole drill. Okay, so we're gonna keep the table horizontal to minimize the effects of gravities on the trolleys. We're going to polish the table to reduce the friction between the trolley, to minimize the friction between the trolley and the table. We're going to reduce the friction between the trolley and table. The whole procedure should be repeated using trolleys of different masses traveling at different velocity. Avoid using trolleys of very small mass, or you avoid very small values of velocity. Smaller values lead to greater percentage error. So essentially, the gravity one, ensure the table is horizontal to minimize the effects of gravity on the trolley. We're going to polish the table to reduce the friction between the trolley and the table. Another thing we're going to do is we're going to carry out the experiment several times using different values for velocities and different masses of trolleys. And then we're going to avoid using smaller values for the velocities, smaller values for the masses. Smaller values lead to greater percentage errors. So if a ticker tape timer is used, because we want to show a principle of conservation of momentum, U1, we know if it's a uniform velocity, you would observe the following. Yeah, exactly. So you can take 1, 2, 3, 4, 5, 6, 7. You can take how many spaces you want, but they just have to be the same for both. 1, 2, 3, 5, 6, 7. Sorry. 1, 2, 3, 4, 5, 6, 7, 8. No, they'll give us the distances, I'm sure. So now we have work, energy, and power. So we said, first of all, we talked about momentum. P equals mv. Mass velocity, kgms minus 1 was the unit. We said friction. We said friction was a force that opposes the motion of two objects that are in contact. Excuse me. We said for every action there's an equal and opposite for every action there's an equal and opposite reaction. So now we're looking at work, energy, and power. So work is the work. Okay, so basically work is W is equal to Fs, where work is measured in joule, F is measured in the Newton, S is displacement measured in the meter. So the unit, the definition of the unit is 1 joule equals 1 Newton by 1 meter. Yeah. Calculate the work done when a force Fs. So force of 6 newtons and multiply by 10. So my work done is 60 joules. Yeah. Calculate the work done to move an 15 kg object from the bottom of an incline to the top is, of course, W equals Fs, right? But I'm thinking something. I'm thinking F can be replaced with MA and then displacement. Oh, so they've given us that. Okay. So this is, okay, displacement. So we have W and then S. So is equal to mass. So my mass is 15. It should be okay, fine, 9.8. And then my displacement was 10. So I'm just guessing here. I could be completely wrong. So if I have 150 multiplied by 9.8, I should have, that looks right. 1470 newtons. Sorry, joules. Oh, because it looks like the gravity one. W equals mg, but it's W equals fs. Sorry. So it says a 20. It says a 20 kg object is initially at rest. So u is equal to 0, and it's 20 kgs, and it moves 120. Its speed is, calculate the work done. So we need an a. We need calculate. So this is a horizontal motion. This is linking in the different things. So u is equal to 0, v is equal to 30, a we don't know, and s we know is 120. We go v squared equals u squared plus 2as. So 900 is equal to 2 as. So then I was like, okay, 900 divided by 240 is equal to a. So 900 divided by 240 is equal to a is equal to 3.75 meters per second. W is equal to fs. So W is equal to fs. So fs is equal to, f is ma. So ma is 20 by 3.75 and then by 120. So work is 20 by 3.75 by 120, which is 9,000 joules. It's probably wrong, man. Oh, it is. Shit. So okay, so energy is the ability to do work. The unit of energy is joule. Conservation of energy states that energy cannot be created nor destroyed. It can only be changed from one form into another. And kinetic energy is, so energy kinetic is equal to a half mv squared, where m is equal to mass, v is equal to velocity or speed. Potential energy is E potential is equal to mgh, where m is equal to mass, g is equal to acceleration due to gravity, and h is equal to height. So that's that. E equals mc squared. We haven't done that yet, so I'll just ignore that. And then power. So power is equal to work done per time. So power is measured in the watt. So 1 watt is equal to 1 joule over 1 second. So power is work over time. So 1 joule over 1 second is 1 watt, mgh. And percentage efficiency, if they ask for the unit, yeah. So it says percentage efficiency is basically my output over my input multiplied by 100. So if I have my output, how much am I giving out and how much am I putting in? So my output over my input multiplied by 100. So we have basically calculate the change in the kinetic energy. So we say a mass is moving at a speed of 10. So we have sample question 4. So we have 3 kgs as moving at 10, and it hits and coalesces. Coalesces to stick together with a stationary mass of 2 kg. So right now we have a half m, and we have v squared. V squared is 10 squared. Okay, so we have 150, because 3 by 10 squared is 300, divided by 2 is 150, is equal to 5 over 2 v squared. I multiply both at 300, and then I divide by 5. Find the square root of that is equal to v. Square root of 300 divided by 5 should be... Yeah, so I got V is equal to 7.746. So then I have half by 5 by 7.746 squared. So I have half by 5 by 7.746 squared. So I have 150.00129, and I had 300. I had, let's calculate the change in kinetic energy. Okay, so it says that. Okay, sorry, I completely messed with the question. So I have this. Okay, so I'm going to use the momentum. So this is linking in momentum. Okay, I need to think from that lens. So if I have 3 by 10 and it coalesces, so it has 0 by 2, it coalesces, which means that the masses are now the same, but the velocities are the same, and we add the masses. So I'm like, okay, 30 is equal to 5v. V is equal to 6 meters per second. Right. Excuse me. So I said EK is equal to half. And initially it was 3 was the mass, and it was 10 squared. Then I have EK, which is equal to a half. Now the mass is 5 and is moving at 6 squared. So that's equal to. I just want half, and then 3 by 10 squared is 150. So that's 150 joules at the start, and then we came up with 654. No, sorry. Oh no, it's not. Okay. Wait, that was close. It's 90. So 90 joules. So really the change is 150 minus 90, which equals 60 joules. That's my change. Then I have something like this. So it's like a pendulum bob is released and allowed to swing. The bob falls a vertical distance. So essentially I have something like this. So this is H. So this is 0.15. So we have mgh equals a half mv squared. We can cross out the masses because both sides have mass, so we can just divide that. 9.8 by my height, which was 0.15, is equal to a half by v squared. Then I can just get rid of this whole half, multiply this side by 2, and get the square root. So v is equal to the square root of 2 by 9.8 by 0.15, which is 1.715 ms minus 1. And then it's like, then it's like, okay, a bullet of mass. The speed of, so this is momentum, I'm thinking, because 2 grams and speed of 5. So 0.002 is multiplied by 500 and it hits a stationary piece of wood, which is going to be 0, and that's 1. And that means that they're going to coalesce, which means that their mass becomes the same, which means that it becomes 1.002, and that means their velocity becomes the same to v. So it says we need, oh no, they do not become the same thing. Good thing I spotted that. It said that the bullet emerges from the, so the bullet, so that's 0.002 by 100 plus v, because it's just 1 anyways. That's the mass, so v. So then I'm like, okay, so I'm like 0.002 multiplied by 500 minus 0.002 multiplied by 100, which is v is equal to 0.8 ms minus 1. Is that correct? It is, yeah. And then it's like, okay, the speed, the height the wood rises. Okay, so we have something like this and this, right? So we have the wood is suspended by 2 meters long. H is my x. Yeah? Yeah. So we have mgh is equal to a half mb squared. We have m on both sides, we can cross that out. We have 9.8 by h, and that's equal to a half, and we have the speed, which is 0.8 squared. Yeah, so then we have h is equal to a half of 0.8 squared divided by 9.8. So h is equal to, we have basically a half of 0.5 by 0.8 squared all over 9.8. So I got 0.03267 meters. Okay, I don't know if that's correct now. But then it says the height the wood rises. So the whole thing's 2. That little distance there. Oh, that's 2. The height the wood rises is going to rise from, yeah, it's going to rise from there. And the angle to which the bullet moves, which is just this angle here. But bro, 2 meters string is this, not this, this. So then I have something like this, I have 1.96733, and I have 2. And this is my adjacent, this is my hypotenuse. So I have cos theta is equal to adjacent over my hypotenuse. Theta is equal to my cos inverse 1.96733 all over 2. Theta is equal to my cos inverse of 1.96733 divided by 2. So that's 10.37 degrees. Yeah, 10.4 degrees, exactly. So essentially the speed of the wood momentum is easy. The height would rise, we find h, but we actually want x, so we just minus that. And then angle to which, so the 2 is the string itself, yeah. So it's like, okay, a sample question 7. It says that the pendulum in the diagram is 8 meters long with a bob. So yeah, okay, so this is 8, and this bob here is 6 kilograms, and this here is h, this here is x. Oh, so we calculate h, we wanted x. Ah, okay, that makes sense. So this angle here is 30 degrees. It says calculate the height to which the bob is. Yeah, sure. So mgh is equal to a half mv squared. Conservation of momentum. Energy cannot be created, destroyed. It can only be changed from one form to another. So we're changing from potential to kinetic. Calculate the height to reach the bottom. So G is 9.8. Height we don't know. Oh shoot. Never, my bad. I don't need to do all of that. I can just do cosine of 30 degrees is equal to adjacent over hypotenuse. 8 cosine of 30 degrees is equal to this. 8 cosine 30 degrees. So I'll just go at 4 root 3 is equal to h. And I'm like 4 root 3. What would be longer, 8 or 4 root 3? I think 8. So 8 minus. Yeah, so 8 minus 4 root 3 is equal to 1.07 meters. It's going to be 1.07. We can just go 1.0718 meters. Yeah, so the bob is then, and then the potential energy it has. So now that we have, so that's x, yeah. Then I have, I'm like, okay, 9.8 by, so what's h? Is h is this whole thing here? Or is h this? 1.0718 is equal to a half by m and then v squared. Oh bro, what am I? I'm actually fumbling. EP is equal to 6 kgs by 9.8 by 1.0718 multiplied by 9.8 multiplied by 6, which is equal to 63 joules. Yeah. That's like, okay. That's like, okay. No, but then why was the height? No, the height. This is stupid idiot, man. This is x and this is h. Okay. At least I know now. What's the maximum velocity it attains? mgh is equal to a half mv squared. m's get crossed out. 9.8. My height is, nah, it's h, bro. 1.0718. So h is on the bottom. And then it's equal to a half of v squared. We get rid of that, multiply this side by 2 square root that, we get rid of that squared. So I get basically square root of 2 by 9.8 by 1.0718. 1.0718. 2 by 9.8 by, I get v is equal to 4.58 ms minus 1. And it says when the bob moving in position A, when the moving bob is at position A, a force is applied between the bob to stop a distance of, when I feel like I missed the question. That was a very interesting question. So sample question 4, sample question 5. And it was like, okay, when the moving bob is at position A, so here, a force is applied which brings the bob to stop in a distance of 5. So v squared equals u squared plus 2as. Well, we have u, which is equal to 4.58, was it? Yeah, 4.58, yeah. So 4.58, v is equal to 0, a is equal to 9.8, s is equal to 5 by 10 to the minus 3. So 0 is equal to 4.58 plus 2 by 9.8 by no, we don't know the acceleration. Minus 4.58 divided by 2 by 5 by 10 to the minus 3 is equal to a. So I got minus 4.58 all over 2 by 5 by 10 to the power of minus 3. I forgot to do something. I was like, why is the value so big? Yeah, it's 209. Yeah, so a is equal to 2097.64 multiplied by 6. We get 12585.84 newtons. Yeah, so yeah, okay. There's a question, man. I swear, it's like I don't know. It's like the potential energy is equal to the energy and the energy. Bro, I don't know why it's not in here. Maybe it's in one of the exam questions. Possibly. Yeah, possibly. But it says basically, what is the principal energy conversion? Potential to kinetic. Ignoring friction, calculate her maximum velocity when she has traveled 400 meters. A maximum velocity is probably going to be mgh is equal to half mv squared. We know her mass, but we don't really need to do all that. So 9.8. Her height, her loss of elevation was 90 is equal to a half of v squared. We remove the half, multiply the other side by 2, we remove the squared, we put the square root, and we find the square root is 2 by 9.8 by 90, which is 42. So v is equal to 42 ms minus 1, and it's a whole number, it's probably right. So she then plowed into snowdrift and came to a stop in a time of 0.8 seconds. What is the force she exerts on the snowdrift? So we need a, basically, yeah. So we have u, her initial velocity is 42, her v is 0, her a we don't know, and her s is equal to we don't know, and our t is equal to 0.8. They're trying to trick you. They want you to put s as 400 meters, but we don't know that. So we have v equals u plus at. So 0 is equal to u plus 0.8 0.8a. Then I have minus 0.8. No, so then I have minus 42 divided by 0.8 is equal to a. A is equal to, so minus 42 her mass is 71, so multiply by 71 and I get minus 3727.5 newtons. I definitely got 727.5. Do we need the minus? Yeah. So she exerted a force of 3725 newtons. She exerted a force of 3725 newtons on the snowdrift, and the snowdrift exerted an equal force of 3725. So if she exerted this force, the snowdrift's going to exert the same force in the opposite direction. So minus indicates opposite direction. So if we have a minus, we're going to get plus then. Yeah, positive value. So we have different types of energy. We have kinetic energy, potential energy, heat energy, sound energy, light energy, electrical, chemical, nuclear, all sorts. Energy conversions. We have electric to kinetic. For example, when we have a motor, we can have electric to sound. For example, when we have large speaker systems, we can have kinetic to electric. For example, when the wind turbines, which produce electric to kinetic, electricity is used to rotate an electric motor. Chemical to kinetic, chemical, electrical to chemical, already electrical to sound. Yeah, renewable source of energy is like, first of all, trees. So hydroelectricity, converting kinetic energy of flowing water to electricity. Solar energy is converting the sun's energy to heat water in a solar panel or generate electricity in a solar cell. Wind energy, large wind power generators convert kinetic energy into electricity. Biomass, energy extracted from biological materials, e.g. the burning of wood. Remember that trees can be replanted. So renewable sources of energy, these are forms of energy will never run out. So hydroelectricity, solar electricity, biomass, wind turbines or wind energy. Non-renewables like coal, turf, oil, gas. These are forms of energy that will run out, that eventually be used up, and the fossil fuels can be included on this list. And the sun. So the sun. In the sun, mass is converted to energy process called nuclear fusion. This will be studied in later stage. So yeah, renewable hydroelectricity. We're using the flow of water to produce electricity. We have wind energy, where the wind rotates a wind turbine, which makes electricity. We have solar energy, which is the sun's energy, heats either water in a panel or generates electricity. We have biomass, where like biological materials, energy extracted from biological materials such as burning of trees, and we know that trees are renewable as they can be replanted, right? And renewable sources of energy are energy sources that will not be used up, whereas non-renewable energy sources are sources of energy that will eventually be used up, and they're limited, that they'll eventually be used up. But I'm gonna, so that's good. Oh, sorry, that's not the chapter I studied. I studied this chapter, and then I'm just gonna put, I was actually gonna bail. I still need to do PPQs for that. So yeah, alright guys, that's it for today's stream. That's 2 hours of deep work done.